Good afternoon, everyone. Welcome to the second live session of Basic Linear Algebra. So let's begin with recollecting what we have done in the last week. So first we saw what is variable elimination method. Then we saw the possible solutions like what does it mean if it is having single unique solution or infinite solutions or no solutions at all, with example of lines and planes. And then we saw some basic matrix operations. And their properties. We saw Gaussian elimination. We saw what is row echelon form. And we saw how the based on the row echelon form, how can we comment on the solutions, whether it is unique or infinite or no solutions at all. So if rank is equals to number of columns, then we are going to have unique solution. If rank is less than number of columns, then we are going to have infinite solutions with n minus r as arbitrary variables. And if we have a zero rows corresponding to which we are having a value on the right side, then we are not going to have any solution. It's going to be inconsistent. I hope you have gone through the lectures, recorded lectures by the professor. So let's summarize what was said in what was taught in that. So this is so row echelon form, as we saw. Some values here. So if this is the pivot, then the first non-zero number in the row, then then in the next row, subsequent row, the non-zero pivot should be in the column which is to the right side of the pivot column in the previous row. Something here. So if in the first column, in the first row, if so in the first row, if the pivot is in the second column here, then for the subsequent row, the pivot column should be on the right side. Likewise for the subsequent rows below, here some values will be there. So if it is like, it should be like this, and there will be some non-zero rows. There can be some non-zero rows in the bottom. So R is the number of non-zero rows and number of pivots also, and m minus R will be the zero rows. Some examples were solved in the last class. So how this is done in for example, if you want to do some programming or anything for standard methods, how this is done is from the elementary matrix operations. So for example, if Eij is the interchanging row interchange matrix. So if I want ith and jth rows to be interchanged, then we can show it from the identity matrix. Another is multiplication of ith row by a scalar, non-zero scalar value. And also one of the elementary operations is adding a row with a scalar multiplication to another row. So these were the basic operations which we saw to get any matrix to the row echelon form. So now reduced row echelon form was taught in the lecture. What is reduced row echelon form is in row echelon form, the pivot can be of any value, but in reduced row echelon form, what we do is we make all the pivot values as 1, and in row echelon form, all the values under the pivot in a column will be 0, but in reduced row echelon form, all the values in the column above the pivot as well as below the pivot, everything will be zeros and the pivot will be 1. So that if we reduce in that form, that is called row echelon form. So row echelon form is not unique, but reduced row echelon form is a unique for any matrix. Then the inverse of the square matrix was also explained. So if a square matrix A is invertible, which means that there exists a B matrix such that AB equals to BA equals to identity matrix. So here A inverse is a unique. A inverse is unique. The properties were discussed, like A is unique, and if A and B are invertible, then AB is also invertible. And all the elementary matrices which we discussed before are invertible matrices. So if a matrix is given, how can we say that the matrix is invertible or not? And if at all if it is invertible, then how can we derive the inverse of the matrix? So if a matrix A is given, how can we say that it is invertible matrix is? We'll try to reduce it to the row echelon form. Reduced row echelon form. So notation is REF is reduced echelon form, and RREF is reduced row echelon form. So we'll try to bring it to reduced row echelon form, and if it is identity matrix, then that is invertible. If it is not, then it is not invertible matrix. And how to inverse the matrix is, we will augment A and identity matrix, and we will make row operations, elementary row operations, so that A will become I, and correspondingly this will become we'll get a matrix here which will be inverse of the A matrix. Further, some more points were discussed, like if we have set of equations like this, then if rank of A matrix is less than rank of A augmented B, then the system is inconsistent and we will not have any solution. If if the rank of the matrix is equal to number of columns also if the rank of the matrix A is equal to rank of the matrix A augmented B, and if it is equal to number of columns, then we'll be having unique solution. And if rank of A matrix is equal to rank of, but it is less than n, then we'll be having infinite solutions. With n minus r arbitrary variables. Further, the vector space was also discussed. So the vectors in the vector space, so vectors are said to form a vector space if it is at least having one zero, if it is having a zero vector, and also the for example, vector, these are the vectors. Then these are said to form vector space if there is a zero, vector in that in the set, and also if the linear combination, even this should be in a set of the vector space. So we'll see the examples to understand this better. And also first thing is there should be zero vector. Second thing is addition property, addition of the vectors should also be in the space. Third thing is the scalar multiplication. Should also be in the set. So if these three conditions are satisfied, we are saying that the vectors form the vector space. So with this, let's solve the examples. I ask you to solve the questions along with me and let me know if you have any doubts.
Excuse me, ma'am.
Yeah?
Ma'am, could you please explain what is the basic difference between
Sorry, I didn't get you.
Between reduced.
What is reduced row echelon form and reduced echelon form? Is that what you
Yes, yes, ma'am.
Okay. Okay. So so row echelon form, let's see that first. So we'll be solving even examples which will make your question even more clearer for you. So in this, suppose there are some zeros in the starting, and we'll have and some numbers here. This is a pivot, and here it will be like the pivot in the next column in the next row must start with a column number which is more than the column in the previous one. So suppose if it is like this, some numbers again here. Some numbers here like this. So this is some non-zero, some zero rows in the bottom. So if this is the row echelon form, But so any values can be there. So a1, p1 can be any values. So there's no constraint on that. a1, p1, a2, p2, they can be any values. The main difference here is reduced row echelon form. What you'll try to do is you will make this pivot as 1 and some values here, and these are also pivots. So you'll try to make this value as 1, and what are the values above this, whatever values in this column above the pivot, you will try to make them also as 0. Initially there can be some values here, and some value for the pivot, it need not be 1, and this need not be zeros. The columns above the pivot need not be the values, the row values in the column, pivot column above the pivot value, they can be any values, but here they will be 0. You try to reduce them. So anyways, I hope I will solve some examples which will make this reduced row echelon form more clear for you. So here you see we have we can have some values here, any values here, but in reduced row echelon form we'll try to make it as 0. Do you understand?
Yes, thank you.
So we'll try to solve some questions on that, so that this gets more clearer to you. So try to find the rank of the matrix. This thing, I'm showing the matrix here. Try to find the rank of the matrix. So as I said, if you have a matrix, what we will do is first of all, the inverse exists or not, we can say it by if we are reducing this matrix to reduced row echelon form, then if we are getting identity matrix, then that will be A is invertible, and if I want to find the inverse of the A matrix, then I will augment matrix. I will do row operations such that I will convert A as I, and whatever matrix I am getting here, this will be inverse of A. So what is the first step here? So we have a 0 here initially, so we will interchange. So doing operations. One, 0, 5 by 3 in the first row. Further, I want to make this element as 1, so R2 by 3 will give me as I said, reduced row echelon form. So we got a pivot here. So all the values, row values in the column must be 0. So even this has to be 0. So to make that as 0, so we'll get in this way. So can we reduce this matrix further?
No.
We cannot. We have a 0 row in the below, and we cannot reduce it further. So number of columns here is 3, but rank, what is the rank here?
2.
Rank is 2. Yeah, so rank is 2 here. So can we convert this? So can we find the inverse for this?
No.
Yeah, so we cannot find the inverse for this. Likewise, let's go for the next question. Okay. So just to simplify this, I am dividing the whole thing by 2. So we can divide each element by multiply any scalar with the rows. So that will not change the entire meaning of the matrix. So divided the entire matrix by 2. So what can we do here? I want reduce row echelon form of this and see whether I'm getting the identity matrix of 4 by 4. First of all, let's find the rank of the matrix. For that, reduce it to get into reduced row echelon form. So I'm doing operations. So if you directly subtract this, we are going to get this as 0. So if you directly subtract 6, this will be minus 6.
Zero, minus 12, minus 30, minus 63.
Yeah. Further, on doing this, we are going to get so I interchange this 2 rows. So this is reduced echelon form. Do you understand? So this is in the form like all the pivots. See, the column number is increasing, so P1 is more than, P2 is more than, so this is strictly increasing. So this is reduced echelon form. To get, this is row echelon form. To get it into reduced row echelon form, what are we going to do? We'll make all these values as 1. All these pivots values as 1. We'll do the row elementary operations to make this pivot values as 1, and corresponding, and the values above the pivot, even above the pivot, all these things, they should be 0. We will make elementary operations to make these as zeros. Then whatever we are going to get is in the reduced row echelon form. So first thing what we are going to do is row 4. Row 4, if you are dividing by minus 15, we'll get this as 1, and then so we'll make this row 4 as row 4 by 15. So we'll be getting this thing, and then I want to make this as 0.
Minus
So row
15
2
it
will
should
be
be.
going to row 2 plus 63 into row 4, and row 3 will be going to row 3 plus 75 by row 4. So we are going to get
Minus 15. Yes, ma'am. R4 changes to R4 by minus 15.
Yeah, so now I want to make this as 1, and the columns above it as 0. So row 3 goes to minus 50, and row 1 goes to row 1 minus 4 into R1. So we'll be getting as 1, 2, 0, 0, 0, minus 12, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And finally R2 is going to R2 by minus 12, and R1 is going to R1 minus 2 into R2. Then we will be getting So what is the rank of this matrix?
4. Invertible also.
So rank is 4 and this is invertible, yeah. So what does the rank means? It means that we have the rank is 4. It means that we have 4 independent rows. What is let's solve some questions based on the linear dependence. So for example, if I have a vector like this, let's go to another question. So solve and tell me whether these vectors are linearly dependent or not. So so let's see, like if they are linearly dependent, then there must be some scalars, non-zero scalars, such that suppose if I'm saying this A and if I'm saying B and this is C, then if I'm able to find some alpha and beta such that I'm getting this kind of relation, then that is linear. Then they are linearly dependent. So for example, if alpha is equal to, just by seeing we can see if alpha is equal to 2, then the so we are going to get this thing correct, and if beta is equal to -3, then even this thing will be satisfied. So if I substitute alpha into 3 plus beta into 2 is equal to 0. So suppose if this, I'll just check for this, if this is 0, yeah, so even for this it's so 2. So this is 8. So alpha is 2 and beta is equal to -3. So whether this is linearly independent or dependent?
Dependent,
Linearly
ma'am.
dependent.
Yeah, so they are linearly dependent. Similarly, solve for this. If we have vectors like this, then let me know whether these are linearly dependent or not. For example, let's take this thing. Because I'm naming in this way. I'm just talking about this elements. trying to find, I'm just guessing some values like suppose I'm taking alpha as minus 6 into b1 is 1 by 2, beta I'm taking as 6, and this is 1 by 3 c1, and gamma I'm taking as 8, so I'm getting here 1. So suppose I'm taking alpha as minus 6, beta as 6, and gamma as 8, then that's satisfied for the first elements. So suppose if I'm substituting the same thing for the next row, so it is not equal to 1 by 2. So what can you say about this?
Not satisfied, so it would be linearly independent.
Yeah, so it's independent. So if you can express any one of the vectors in terms of the linear combinations of the others, then we can say it as linearly dependent. If we are not able to express in that way, then they are linearly independent. Try to find the inverse of this matrix. And next we are moving on to next question. Try to find inverse of this. So what are we going to do first? So we'll augment with identity matrix here. We will do row operations such that this has become identity matrix, and whatever corresponding value we are getting here, that will be inverse. first of all, let's try to make this as 1. So for the okay,
Madam, directly we can solve
yeah,
R2 changes to R2 plus 5R.
I didn't get you. Yeah, so anyways, that is there. For this, let's multiply R3 by 3 so that this will become 1.
5R1.
5R1. Yes, sir.
3R3 plus 5R1 will serve the purpose for making that element 1.
Sorry, I didn't get you. Yeah, there are multiple ways of doing this. So now if I'm going so we got the pivot values here. Now I want to make all these columns above this pivot as 0. So if we are going with R1 as R1 minus R3, then we are going to get this matrix. So this column is sorted. Now I have one value here and one here. Now I want to make this as 0. So for this, if I am making R1 as R1 plus R2, then even this is sorted. So now I want to make this as 1 because I want to convert this as identity matrix. So if R1 is going to R1 by 3, then we will be getting as I said, this will be the inverse of the matrix with which we started. So someone has any question?
No, ma'am.
Someone raised hand. this is the inverse of the matrix which we started with. Is there any question here? The detailed explanation of why this method will work is already explained in the lectures. Let's take another very simple question. What will be the inverse of this matrix?
Identity matrix.
So what we do? What we can do is identity matrix is the inverse of this.
Yeah, if you can interchange R1 with R2.
Yeah. So for making this identity matrix, I need to interchange these two.
Only R1, R2 change will serve, no?
We have to exchange these two. Yeah.
Inverse will be the matrix itself, given matrix.
So here also, if you are exchanging, so this is the inverse, not identity matrix. So you are saying no that the inverse is the inverse. Inverse is the matrix itself. So whatever we are getting here, that is the inverse. We should convert this to identity matrix, and by doing the same row operations on the right side to identity matrix, whatever we are getting, that will be the inverse. So this is the inverse of this matrix. I hope it is clear.
Yes, ma'am, clear. I have a question. May I?
Yeah.
Ma'am, can you please explain what is matrix having full rank?
And matrix having full rank.
Yes.
So if rank of the matrix is equal to number of columns, rank of the matrix is whatever minimum, it's called full matrix, full rank.
Equal to number of columns
It should not have any zero rows. Each column should have a pivot if it is a square matrix.
Okay.
What is your question exactly? Could you repeat your question?
Ma'am, my question is, what do you mean by a real square matrix having full rank?
Square matrix with full rank. Yeah, for example, if it is n by n matrix, square matrix, and if R rank is equal to n, then that is the full rank, like maximum we can have.
Okay. So you want to say if you have a 3 by 3 matrix and if its rank equal to 3, then it is a full rank matrix.
Yeah, if we can convert it into identity matrix fully, then we can say in that way. So we can even invert it.
Okay, ma'am.
Take up another simple question for finding the inverse of the matrix given here. anybody able to find the inverse of this matrix?
No, ma'am.
Yeah, so the inverse is not possible here. Why?
We cannot convert a given matrix into row reduced echelon form.
Yeah, so we
It
cannot
is not
convert this
possible.
first of all into identity matrix. All are 0 here. Rank, we don't have a full rank here. It's not. So we cannot get the inverse of this matrix. So I hope with these examples you understood how to find whether the matrix is invertible or not, and if at all it is invertible, then how to find the inverse of a matrix. Do you have any questions regarding this?
No, ma'am.
Okay. To prove this. If you remember the properties of the inverse, so so this is the property. Anyways, we know this, that multiplication of a matrix by its inverse will be equals to identity matrix. And if I take the whole inverse for this matrix, A into A inverse the whole inverse, that's anyways the identity matrix as we know. And by the property that if AB inverse is taken, then provided both A and B has to be invertible matrix here, anybody having any doubt in this?
No, ma'am.
Okay. So if a matrix is invertible, what it indirectly means that the rank of the matrix is equal to the size of a square matrix is equal to the size of the matrix. If it is n by n matrix, then rank of the matrix will be equals to n. So let's see some questions on the vector space. So I'll give some examples like given set of vectors form a vector space? If yes, then determine the dimension of it and also tell me the basis. The v1, v2, v3, etc. are the components of the vector. So tell me if with this constraint, will the set of vectors with this constraint will they form a vector space? Is my question clear?
No, ma'am.
So v1, v2, v3 are the components of vector. Suppose v is a vector, then in R3, these are the components and the constraints given are this. So with these constraints, will the vector make the vector space? Let's solve an example for this. So first,
Ma'am, its answer is no.
it's not like that.
Because this should be linearly independent. If v1 is equal to minus of v2, then they may not be linearly independent. So it is.
Okay, let's see this question. So first of all, for a set of vectors to be in vector space, one rule is zero vector must be in that set. So zero vector must be in that set. The set must contain addition and scale. Addition law should be verified. For example, if these are two vectors in the space, then this thing must also be in the space. And if this vector is in the space, then even this vector should be contained in the space. So if we solve a couple of questions, then this will be clear for you. Third thing is, any restrictions that prevents the operation from staying within the vector, within the set. That's not a vector space. So for example, one question, let us take up one question. So for all vectors in R3, such that v1 plus v2 is equal to 0 and v1 is equal to minus v2, with this condition, tell me if it forms the set of vectors will form a vector space or not. So it is R3. We have three components of a vector. So say for example, I have denoted some arbitrary value s for this, and arbitrary value of t for v2. Then as this condition is applied, then v1 will be equals to minus p. So this is the condition for the components of the vector. So how can I write this? So I can write in this way. So, for example, if I make p as 0 and s as 0, then we can get v1, v2, v3 as 0. So the 0 vector is there in the set. 0 vector is there in the set, and these vectors will satisfy the condition, this constraint. These vectors will satisfy the addition constraint. Addition constraint is anyway satisfied because we are expressing this as the linear combination. And these vectors also satisfy the constraints given here. So this will form a vector space with dimension as 2, because we have two independent vectors, and basis are these two vectors. Any doubts in this?
Ma'am, repeat करो how can find the basis of this vector? How can find the basis?
Okay, so first of all, I hope you know what is the basis of the vector space. So what is the basis of the vector space is a basis means like with those linear combination of vectors, we can get any vector in the vector. We can get any vector in the set of the vector space, and the basis is something which we cannot derive from any other thing. Like for example, here I am saying this as basis. So with the linear combination of this thing, the linear combination of this thing, I can get any vector which will satisfy this constraint. But by doing any operation, I cannot get this thing alone. Like this thing I cannot get in any way. I hope you went through the videos, video lectures. Okay, let's take up another example, and then I hope that will be clear for you. So for all vectors, we'll get back to the same example again. Let's solve it multiple times so that we'll understand it. We'll get back to the same question, so don't worry about that. So for all vectors in R3, if these conditions are applied, tell me if the set of the vectors will form a vector space or not. R3 space. So any vector will be having 3 components. So for a set of vectors in the sense some numbers you have to give, whatever numbers you give here, they'll be giving the set of vectors, whether they will form satisfying this constraint, whether they'll form the vector space or not. So that's the question. So first rule, as we said, 0 vector must be a set. So for sure we must have this vector in this set. So let's see whether this condition will satisfy this constraint or not. Okay, so v1 is more than 0, equal to 0. So yeah, so this constraint is, so this is okay, so this is allowed. And if suppose v2 is equal to 0, then v3 is equal to minus 1 by 4 of v2, which is also 0. So if this vector will satisfy the constraint for the components given here. Do you understand till here? So this is allowed. So first condition is satisfied. Any questions till here?
No, ma'am.
So first condition is satisfied here. Now we'll see whether the addition will be is that allowed, is it okay or not. Like for example, if I take a vector, 2 vectors I'm taking. Sorry. So suppose I'm taking these 2 vectors in this space, which will satisfy these conditions, I'm taking these 2 things. I'm assuming I'm taking that. So what will happen? So addition. So even the linear, scalar linear combination. I'm taking a simple case. Even this should lie in the vector space. Yes or not? If the set of vectors should be in vector space, even this should satisfy the constraint. So as I said, these are in the space. These are the set. Okay, these are the set which will satisfy these conditions given. So which means that I'm taking 2 vectors which will satisfy the constraint given here. So some linear combination even this should satisfy this constraint if it is in vector space. from this so we already know here from here that so you know this concept second component. So here the second component, say for example call this as some b, okay. So b2 is again minus 4 times of b3. So this constraint is satisfied. Do you understand?
Yes, ma'am.
So addition is for this constraint it is satisfied, okay. Now let's see this constraint. It has to be more than 0 because it's mentioned that v1 is more than 0, okay. So will this satisfy? So for example u, so as I said here u is this will satisfy, okay. So u1 is more than 0. These are two constraints here, okay. So u1 is more than equal to 0, for example. So suppose I'm taking it as 1. And suppose if I'm taking as
U1 plus W1 will be certainly greater than 0, as U1 is greater than equal to 0 and W1 is greater than equal to 0.
so is there any possibility for this to become less than 0?
There is no possibility that it will not satisfy. It will definitely satisfy U1 and W1 greater than equal to 0. So sum is also going to be either 0 or greater than 0.
Fine, okay. So second condition also is satisfied, okay. Now let's come to third condition, that the scalar multiplication, some non-zero scalar multiplication, this is R, so like in the space R, and can be any scalar multiplication. So this, so it's mentioned that, okay, so 0. So for example scalar multiplication of u, so is there a possibility for this to be less than 0? So yeah, u1 as I said u1, u2 and u3, that will be in the space, so definitely u1 is more than equal to 0, okay. But there can be any alpha value which can make this less than 0. For example alpha is some negative value, okay.
Minus 1.
It can be less than 0, okay. So this first element, for example if this is b, for example if I'm taking b1, b2, b3, it is equal to alpha u1, alpha u2, alpha u3. So b1 is alpha u1. So this has to be more than equal to 0, but there can be any alpha which can make it less than 0 also. Do you understand? Possibility is there. So the set of vectors with a given constraint cannot be vector space, cannot form a vector space, because this condition is not satisfied. Do you understand?
Yes, ma'am.
I hope everybody got till here. Are with me? Any doubts?
Ma'am, I have a question.
Yeah, please ask.
Ma'am, all the time we'll be having a linear equations in the condition, or some quadratic or cubic equation will also be there.
Sorry, I didn't get your question.
Like this example you have taken, no? V1 greater than equal to 0 and V2 is equal to minus of 4 times V3.
Yeah, that's the constraint given on the components in the vector.
These constraints are linear constraints.
Okay.
So my question is, will it be there like V2 square is equal to 4 times V3 kind of?
v2 square. So right now,
quadratic constraint.
So right now we are in basic linear algebra. So linear. So let's constrain ourselves to the linear things.
Okay,
v2
so if
square
it is square, then it is not going to be the vector space.
That is another topic. Let's discuss. That won't be in the scope of this thing. Will be in this linear thing.
Okay, ma'am.
There will be asked in the exam also that kind of questions. Because we are dealing with basic linear algebra, so all the terms will be like in the linear form. So it will be linear combinations. So let's get back to the previous questions, because I think that is not very clear for you. Shall I explain the previous one, or is it clear for you?
Clear.
The previous one? Okay, let's solve some more examples. For all the vectors in R3 which follows the condition tell me whether the vectors satisfying the components of which satisfying this constraint, they will form the vector space or not. And if it is forming a vector space, what is the basis and what is the dimension? So basis is a set of independent vectors using which with the linear combinations of which we can find any vector in the vector space, and by doing any combination of the subset, any subset of the basis, we cannot get the vector in the we cannot get the basis, like so as we saw in the previous example, these are the bases. Okay, let me explain the previous example so that the basis will be clear for you. So I said the previous question as let's do this first and get back to this question again. So I was telling for all the vectors. In R3 such that v1 plus v2 is equal to 0. The set of vectors with this constraint, will they form a vector space or not? That is the question. If yes, then what is the dimension? Dimension is equal to the size of the basis, and what are the bases? So R3, so we'll have 3 components in the vector, and the constraint given is v1 plus v2 is equal to 0. So this is the constraint. So first of all, we should see whether 0 vector is acceptable or not in this with this constraint. So if v1 is equal to 0, then v2 will also be 0, because v2 is minus v1, and v3 can be 0, but there is no constraint on the v3, so v3 can be 0. So 0 vector is there. So first constraint we have is satisfied. And suppose if I say this is vector and this is one more vector in the set, then even this thing must satisfy this condition. So even this condition should satisfy. So if I am saying that even this is 0 and this is 0, so this condition is satisfied. Yeah, someone answered basis as -1 1 0 and 0 0 1. That is correct. Why? Because this vector so with the constraint as I can write in this way. So this is the basis. And because we have 2, so the dimension is 2. So this is basis because with any linear combination, the T and S, with any linear combination of these two vectors, I can get any vector in this space which is satisfying this condition. But using any other vectors, I cannot derive this thing. I cannot derive to this vector by any linear combination of anything. For example, from this I cannot get this thing. So you cannot reduce it. Do you understand? From this basis I can get the whole space. But this itself I cannot get. These are independent. I cannot get it. So these are two independent vectors using which I can get the whole space which will satisfy the constraint I gave. But as these are independent, I cannot derive these two vectors using any other vector in the space. So I have two vectors here which form basis. So dimension is 2 and basis are these two vectors. I hope this is clear. So let's get back to the question which we were doing before. So for set of vectors in R3 space, tell me the vectors having this constraint, whether they will form the vector space or not.
Madam, is it -4 0 1 and 0 -3 1, dimension 2?
Sorry, I didn't get. So you are telling the basis?
Yes, ma'am.
What is the basis?
-4
Okay.
0 1 and 0 -3 1, dimension 2.
Okay, so okay, let me keep this aside and let's check whether that's correct or not. So first thing is zero vector, whether there is a zero vector or not. So yeah, so if as I said 4v1 plus v3 is equal to 0 and 3v2 is equal to v3. So if suppose v1 is equal to 0, then even v3 can be 0 from the first condition, and even if v2 is 0, then even v2 can be 0. So 0 0 0 in R3. So there is a 0 vector in R3. So 0 vector in the as per the constraints. So so the first condition is okay. Suppose if I'm taking two vectors and just checking whether the linear combinations is working or not. I want to check whether this condition should satisfy, okay, because it's mentioned that 4v1 is equal to minus v3 minus sorry not yeah, so because this condition is there, so this must satisfy, and 4v1 plus 4w1. So as we know that this condition is given, so this will equate. Just by seeing we can say that. And even this condition even this should be satisfied, and even that will satisfy the summation of, even that will satisfy. So even if we see the scalar multiplication, so alpha, suppose if I'm saying alpha v1, alpha v2 and alpha v3, so alpha v1 into 4 should be equal to minus of alpha v3, alpha gets cancelled and we'll get it. Similarly the other way. So this forms a vector space. I hope this is clear till now. So when 3 into alpha v2 will be equals to alpha v3, because alpha gets cancelled here, and we'll get to the same constraint there. So do you understand that? So all the three constraints are satisfied here. So what are we doing is what are we doing to find whether the whether vectors are in vector space or not. So for any set of vectors to be in vector space, there must be a 0 vector, and the addition must also be there in the vector space. Addition must also be there in the set, actually, not vector space. So if there is 0 vector in the set, and also if the addition is also there in the set, and also the scalar multiplication, all these three things are there in the set, then we call the vectors as the set of vectors as vector space. So here we have 0 vector, the first constraint. We have checked whether the 0 will satisfy the constraint or not. If any if any of the restrictions are such that these three conditions will not be satisfied, then it won't be in a vector space. So we saw whether there will be 0 or not. So 0 0 0 0, we saw whether that will satisfy the constraint or not. It was satisfying, so check. So first thing is right, okay. Now next, we are just taking arbitrary vectors in the space set. Like v1, I am taking some set as v1, v2, v3, and w I am taking as w1, w2, w3. The addition also must be in the space. So I'll be having some b vector which I am taking as addition as this thing, addition of these two vectors. So if I am saying this as b1, if I am saying this as b2, and if I am saying this as b3, even this b1, b2, b3 should satisfy this constraint. So we checked it that 4b1 is equal to minus b3, and also 3b1 3b2 is equal to b3. So we checked this constraint and it's satisfied, and also we saw for the scalar multiplication. So this forms a vector space. Now how to get the basis? So this is an R3 space, so V3 we have, so this is a vector and any vector, and we have the constraint this thing. So suppose if I'm just taking some arbitrary value as t, for example, then V2 will be and V1 will be so if I'm taking t out, so by giving any value of t, I can get all the vectors in the vector space, and this is the basis, and only one basis I have, so dimension is 1. So the question, so I hope Akhil Patel, no? Someone answered saying this thing.
Atish, madam.
Atish, okay, Atish, yeah. So
I have taken 2 arbitrary instead of 1 because both are expressed in terms of V3.
yeah,
I
so
have
you
taken
should
2.
not take
That's
arbitraries because both are expressed in V3. So if you just take
yes,
3,
yes,
then you can get it as, you can get the others. So you
yes,
have only
ma'am.
one dimension, and the basis is minus 1 by 4, 1 by 3 and 1. So
Yes,
is this
ma'am.
clear?
Yes,
Anybody
ma'am.
has any questions, please let me know. So this is somewhat confusing. So let's solve some more questions on this. In a space Rn, if any vector, I'm giving this condition for j is equal to 1 to n. Okay, so if n is equal to 1, then j just will be 1, and if n is equal to 2, then j will be 1, 2, like that. Okay, so tell me whether with this constraint the set of vectors will form a vector space or not. Okay, so to start with, what we'll do, we'll see whether zero vector is okay or not. Zero vector, whether this will satisfy the constraint or not. Okay, so Vj, so for example, row V1, V2, it's in Rn, so Vn. Okay, so for all of this, the modulus is less than 0, so sorry, less than 1. So if all are 0 also, that will satisfy the constraint, right? So there is a zero vector, so the first condition is satisfied. Now I'm taking some vector which is there in the set. Now I want to see whether this set of vectors will form a vector space or not. So obviously what I will do, I will just take the addition. Like this, and I will see whether the individual thing will satisfy the given constraint or not. The given constraint is Vj modulus is less than 1, so all these individual elements must be less than 1. So if I generalize it, modulus must be less than 1. Okay, so just think of some examples for which this may be false. So for example, u1 is less than equal to 1. So for example, if I am taking u1 as 1 itself, suppose I am taking some u1 as 1 itself, I am taking this as 1. So 1 plus 1 will be equal to 2. Is not, it's not following the constraint. So may exceed, right? So the values of uj and wj, though they are following this constraint, but this may not be true. So that second condition, that the even addition has to follow, has to be in this, that is not that should follow the constraint. So this is a constraint which is not allowing the addition to be addition to be this is a restriction because of which the set is not staying in the vector space. Any doubt till here? Is it clear? Shall I proceed?
Yes, ma'am.
Okay. So what I try to say here is, though individual elements were following this, but if I add it and I'm seeing whether the linear combination is lying within the restrictions or not, within that set or not, so that's not happening, so it's not a vector space. If you can see the other, you can see for the multiplication also. So if this is true, but I can think of some alpha. I can think of alpha, though this is true, but I can think of some alpha for which this condition may not be true. So possibilities are there. So the vectors with the constraint, the vectors, this vectors in this space does not form a vector space. Let's solve one final example on one more example let's take. Okay, so this is the constraint I gave. So tell me whether the set of vectors will form the vector space or not. So first of all, I am seeing whether the 0 vector is allowed here or not. So if v1 is equal to 0, then of course v2, v3, v4 and v5 all will be 0 from this constraint, from this relation. So this is a vector, one of the vectors in the set which will follow this constraint. So first condition is satisfied. Second condition is I will see whether the addition will follow the constraint or not. even these conditions, for example, if I'm saying this thing, so I can write it like so this is obviously equal to this and this is obviously equal to this, so this condition will be true. Likewise for all the other things, so addition will satisfy. And scalar multiplication, if you see, even for that, whether this condition satisfy or not, yeah, it will satisfy. So this condition will satisfy. Likewise for every other thing. So all the conditions for a set of vectors to be in vector space are satisfied. So this vector with the components with this so vectors with component with this relation will form vector space. So there will be a basis. So what is the basis? So yeah, so this forms vector space, and what is the basis and what is the dimension of that?
Dimension will be 1.
So if I'm taking as v1 as suppose I'm taking v5 as some arbitrary value t. Okay, let's take arbitrary value v1 as t, then I can write it as t, and this will be
T
like
by
this.
2, T by 3, T by 4 and T by 5.
Yeah, so if I'm
This
taking t
dimension
outside,
is 1.
yeah. So this is the basis using which, by the linear combination of which, we can find all the vectors, all the set of vectors whose components will satisfy this relation. But with any combination of any vectors in the set, we cannot get this thing. Do you understand? That is the basis. I hope you are clear with what is basis and how you will determine whether with a given constraint for the components, whether you can say that set of vectors will form the space or not, vector space or not. So 3 conditions: whether you will check first whether the 0 vector is there in the set, and whether you'll see whether the linear combinations, the addition and the scalar multiplication, even that should satisfy the constraint given. So in that case, the set of vectors with the given constraint will form the vector space, else they are not. I hope you are clear till here.
Yes, ma'am.
Okay, so let's solve a few more examples, like some 10 minutes I think is left. So let's solve a few more examples. So for this set of equations, tell me whether the solution exists or not. Tell me in terms of like I hope you saw in the lectures that rank of the matrix will give so much of information, will give information about the about the solutions, the type of solutions we are going to get. So if the rank of the matrix A is equal to rank of the augmented matrix,
Consistent.
and it is equals to n, then you are going to get a unique solution.
Unique solution.
And if rank of A is equal to rank of B, but it's less than n, then you are going to get unique solution, infinite solutions, and is not equal, first of all, then no solution. It means it actually means that if you have a 0 rows in the column but you have some corresponding value here, then it's going to be absurd, so you're not going to get any solution. So just a simple example I took. So for this you can do it like R2 is going to R2 minus 2 into R1, so I'll be getting 2 minus 5, 23, same thing I'm doing here.
0, 16 and 48, minus 48.
Sorry?
Minus 48 it should be.
Okay, yeah, sorry, okay, sorry.
Y equal to, so it is rank of A equal to rank of B equal
I'm
to
doing
10,
rank 2
unique
and-
solution.
Yeah, it's unique solution. R2 by 16 if I'm doing, then I'm getting further if I'm making it. So further if I'm making it as R1 is going to R1 plus 5 into R2, then and if I divide the R1 by 2, I'll be getting
4 and minus 3 is the answer.
Yeah, so we see here that rank of the A matrix is 2. The rank of this entire matrix is also 2. Minimum of the number of rows and columns. So for a square matrix, right? So it's 2. So here, so this is the condition. The rank of the matrix is equal to rank of the augmented matrix, and that is equal to the number of columns. So we are going to get unique solution, which is 4 and minus 3. That we can get it from back substitution method. Okay, now for example, just think you have instead of 6 here you have 10, for example. Okay, instead of 6 you have 10 there. Then what is going to happen? And of course you can get it by, if you multiply row 2 goes to row 2 minus R1 into 2, then you will get 0. Is it okay?
Yes, ma'am.
So what is happening here? This is A matrix, and rank of A matrix is 1. Okay, because you have a 0 rows in the bottom. But if you see augmented matrix, it can be like
2.
even this thing you can consider, right? So augmented matrix, the rank will be
2.
2. So rank of A matrix is not equal to rank of augmented matrix. So we have no solution for this. Which means like this is absurd, because 0 into suppose x, 0 into x plus 0 into y is going to be minus 48. 0 is equal to minus 48. That's absurd. So we are not going to have any solution in this. So now take another example. Suppose if this is I am saying you are having this 46, for example, then
Infinitely many solutions.
yeah, So you can reduce it to this, you can reduce it to this thing. So here rank of A is equal to rank of augmented matrix, but it is less than n. So we have one arbitrary value, and other variables variable and other variable can be defined based on that. So this condition which I was telling, so I have explained with the examples here. So if you have any doubt, kindly ask.
Ma'am, in second example, 2x minus 5y equals to 23, 4x minus 10y equals to minus 2. This next is how to know the A by B, mane augmented matrix ka rank is 2. How it should know?
Augmented matrix का rank is 2, मतलब yes, you can just solve for this. For example, minus, so for example here it is, we have 2 minus 5, 2 minus 5, 23, 0, 0, minus 48. This is the augmented matrix we have. So for this anyways, for this rank is anyways not 2, it's 1. So so you can take anything, like any combination, like this 2 columns or these 2 columns, for example, if you are taking. Then if you make, for example, row 2 as row 2 by 48, then you can get it as 1 here. And then if you make row 1 as row 1 minus 23 into row 2, then we can get it as and here if, for example, row 1 is going by this operation, then we'll be getting, so here we have identity matrix, so the rank here is 2. But rank of A was 1. Is it clear?
Yes, ma'am.
Yeah, so rank of A is not equal to rank of B. In this case, you have inconsistency because the number of this actually means like 0 into x plus 0 into y is equal to 48. So 0 is equal to 48. It's absurd. So in which it actually means that. So so from the rank, you can comment. You will get the information, and you can comment on the solutions which you're going to get. Any other doubts?
No, ma'am.
Okay. So to summarize the session. So first of all, we saw what was taught in the last class, and then we saw what is reduced row echelon form. In which the same row echelon form, if you are converting it such a way that the pivots all are becoming 1, and in the pivot column all the elements in the row above the pivot column, those, if they are also zeros, then that is called reduced row reduced echelon form. And all these elementary operations, if you want to do some programming in a computer or anything, then all these things are done from the elementary operations using identity matrix, Eij, E alpha I, and Ei plus alpha j, like this. And then we saw that row echelon form may not be unique, but reduced row echelon form, that will be unique. And then we saw what is the inverse of the matrix. that for any matrix A, if it is inverse, then there exists B matrix such that BA and AB is equal to I. If this is satisfied, then we say that inverse of the matrix exists, and so this is the condition for inverse, and A inverse will be unique. And to know whether the A matrix is invertible or not, we will try to reduce it to the identity matrix, and if it is we'll try to find the reduced row echelon form for the A matrix. We'll try to make it reduced row echelon form, and if that is identity matrix, then you will be getting which means that the matrix A is invertible. And if it is invertible, how can we find is we'll take augmented matrix like this. We'll try to convert this to identity matrix, and whatever row operations we are executing, the same thing we'll execute for on the right side to the identity matrix, and whatever matrix we are getting, that will be inverse. And then we saw when the system is consistent, whether the rank of the matrix based on the rank of the matrix of A and A augmented B. So if they are equal, then only we'll have the solution. If they are equal, rank of A is equal to rank of A augment B. If they are equal and that they are equal to n. First of all, if they are equal, then only we'll get the solutions. If they are equal, then only we'll get a solution. In these two possibilities are there. If it is n number of columns, then we'll have unique solution. If that is less than n, then infinite solutions. With n minus r, arbitrary values, arbitrary variables, and if this is not satisfying at all, it is not equal at all, then you have no solution. And then we saw vector space. So we have to see three conditions. For set of vectors to form a vector space, the constraint whatever is there, we must first check first there is a zero vector or not. Whether zero vector, that will satisfy the constraint or not. And we'll see if these two are the vectors in the set. Then even the addition or even the linear combination, even that it has to satisfy the constraints which we saw, whichever is imposed on the components. Even this has to satisfy the constraints which are imposed on the components. And the scalar multiplication. This is addition. So if u and v are suppose the vectors in the set which will satisfy the conditions imposed on the constraints, then even so if this is a vector, if this is the v is a vector in the space in the set satisfying the constraint, then even this should satisfy the constraint. So if all these three conditions are there, then we can say that the set of vectors will form the vector space, and then we can find the basis also, and the number of basis vectors we are getting, that will be the dimensions. So that's what we discussed in today's session. I hope you are clear with this. Yeah, so let's meet in the next session on Sunday 3 p.m. Thank you so much.
Thank you, ma'am.